Okay, in this lecture I'm going to talk about the stability of linear systems, a very important concept in control systems, because the first thing you should check when you design a controller for a system is to see if the system is stable, if the closed loop system is stable. So to begin with, we need to define the stability. And I should mention here that there is not only one definition for the stability of linear systems, but the one we work in this course is called the BIBO stability, or bounded input, bounded output stability. According to the definition, a system is stable if every bounded input yields a bounded output. I should actually emphasize this every here, which means that if you want to prove the stability using the definition, you should try all possible bounded input. And if the output to all those inputs is bounded, then system is stable. Similarly, we can define the instability of systems, but this time is a bit simpler to define. A system is unstable if there exists at least one bounded input which yields an unbounded output, which means that if you can find a bounded input that gives you an unbounded output, it is enough to say that system is not stable. I used the word bounded here a couple of times, so I need actually to show you or to define the boundedness of a signal. So what signal we call a bounded signal? According to definition, a signal u of t is called bounded if and only if, for all times greater than 0, the absolute value of u is less than m, where m is a limited number less than infinity, and of course it is positive because we are talking about the absolute value of u. So this definition means that a signal is bounded if you can find a limit for that, if you can find a limited value m such that signal is always less than m. And remember, m cannot be infinity, it should be limited, it should be less than infinity. Let's see some examples for the boundedness of a signal. The first example is a step signal. I'm going to show that the step signal is bounded. It's easy to show because as you could see, the step signal is okay. Of course, it's 0 when time is negative, and it is alpha when time is positive. And by the way, alpha doesn't have to be 1. If it is 1, we call the signal as a unit step, but in general it could be alpha. And as you could see, it's easy to find a limited number such that this signal is always less than below that limit. For example, you can say m is 2 alpha, or even alpha itself, because even if you select alpha, then signal is always less than or equal m, when m is limited. So this step signal is a bounded signal. If we take a look at the ramp signal, so the ramp signal is 0 when time is negative, and it is alpha times t when t is positive. And again, alpha doesn't have to be 1. If it is 1, we call it the unit ramp. But okay, this alpha t, as you could see, it is not possible to find a limit for that, because when the time is increasing, then the signal is increasing as well, and when time goes to infinity, then the signal is infinity as well. So you cannot find any limited value for m such that this signal, the ramp signal, is always less than m, because it is actually tending to infinity. And it's not difficult to prove that sine wave is bounded, because if you have a sine wave, always you can find a limit for that. For example, if it is a unit sine wave, which has the amplitude equal to 1, then m could be selected as 1 and it's always less than that. But if it is a general sine wave, then m is actually the amplitude of signal, and then the signal is bounded. So this was for the boundedness of a signal. Now we can see some examples for the stability of systems. The first example I have considered here is a transfer function 1 over s. I'm going to investigate whether this system is stable or not. And as I mentioned before, to prove the stability, you should try all possible inputs. But let's start with a step input. So we apply a step to this system and we check whether output is bounded or not. Now already we know that the step is bounded because this stability is called bounded input, bounded output. So step should, the input should be bounded, and then we should check output. We know that the input is bounded. So to find y of t, what we could do, we can use the Laplace transform. So y of s, the Laplace transform of y of t, is actually g multiply u. So g of s multiply u of s, and g of s is 1 over s, and u of s is the Laplace transform of the step, which is 1 over s as well. So what you get for y of s is 1 over s squared, and if you take the inverse Laplace from this signal, from this 1 over s squared, what you get is y of t is actually t is a ramp signal, and we showed that the ramp signal is not bounded. So which means that we applied a bounded input, but the output is not bounded. So we can conclude that g of s is not stable. So 1 over s is not a stable system. Okay. For the next example, I have considered a more general case when we have a transfer function with 2 poles and 1 0, and the poles are at a1 and a2. System has 2 poles at a1 and a2, and 1 0 at b, and we want to investigate the stability. Again, if we want to prove the stability, we should try all inputs, all possible inputs, but let's try one of them, which has this form. Suppose that u of t is e to the power of alpha t, e to the power of at, and t is positive. First of all, a cannot be positive because input is supposed to be bounded itself. If a is positive, basically the signal goes to infinity. A is negative, so we are assuming such an input with negative a, which gives you this curve. By the way, if a is 0, then e to the power of 0 is 1, then it is a step input. But what we consider here is actually a is negative. So let's see what would happen when a is negative. So what you get, you should actually find y of t for such an input. So the way to do that, we follow the same procedure that we had for the previous example. We take the Laplace transform of y. So y of s would be g of s multiply u of s, and g of s is this transfer function multiply u of s, and you know that the Laplace transform of e to the power of at is 1 over s minus a. So y of s has such a form, and the next step is actually to find the inverse Laplace transform of this transfer function. And to do that, we should write this transfer function as the summation of 3 terms. So we have these 3 terms here. So b1 over s minus a1, b2 over s minus a2, and b3 over s minus a. And if we take the inverse Laplace transform of this of y of s, we get y of t is b1 e to the power of a1t. This is the inverse Laplace of this term. And the same, we have b2 e to the power of a2t, and b3 e to the power of at. So the output has three terms. Already we know that the last term is limited because the input was limited, so the last term is limited. And this b3 actually doesn't change the boundedness because e to the power of 80 has such a curve, and if it is a scale with b3, if b3 is positive, if b3 is greater than 1, it will be scaled up, and if it is less than 1, it will be scaled down. But anyway, it will remain bounded. So what we should investigate is whether these two terms are bounded. So I will actually check the first term, and whatever we conclude, we can extend it to the second term as well. So the first term, let's see what is. Let's plot the first term. If a1 is positive, the first term will have such a shape, and if a1 is negative, it will be something like that. So in order to have a limited output, a1 should be negative. Otherwise, this term goes to infinity, and it's not limited, it's not bounded. The same for second term. So in order to have a limited output, in order to have a bounded output, a1 and a2 should be negative, which means that the poles of the system should be negative, or in other words, they should be in the left side of the j omega axis. So through one example, actually I showed you, to have the stability, it is a necessary condition that the poles of the system should be in the left half plane, left side of the j omega axis. But it was, we actually tried only one input, but you can prove that, or also you can see the proof in the book. I will not prove it here, but we can prove that in order to have a bounded output, all poles of the transfer function should be in the left half plane. So it is not limited. It is not limited to this specific input. In general, to have a stable system, all poles of the transfer function should be in the left half plane. In other words, the BIBO stability is equivalent to have all poles in the left half plane. So it seems that actually we found a good way to check the stability, because if we wanted to check the stability through definition, it was difficult. We had to try all possible inputs. But here actually we have a better way to check that. What we need is just to find the poles of the transfer function. If all of them are in the left half plane, left side of the j omega axis, then the system is stable. And it is not difficult actually to prove that. If there is only one pole, even one pole, in the right half plane, it is enough to say that system is not stable. So to have the stability, actually all poles should be in the left half plane. Okay, an interesting situation is actually when we have one or some poles on the imaginary axis. So what would happen if some of the poles are on the imaginary axis? I've assumed a system with 5 poles, 3 of them are in the left half plane and 2 are on the j omega axis. And the question is whether this system is stable or not. we can prove that. I will prove it later in this lecture. I will prove that actually when we have poles on the j omega axis, the system is not stable. But this case, actually, we should consider this case as a special case, because as I said at the beginning, there is not only one definition for stability. The other definition for stability, I have mentioned that here, by the way, this system is not stable, it's not BIBO stable. But the other definition for stability is called Lyapunov stability. If you take the COE2 course, over there you will see this definition, and this definition doesn't work with inputs and output. It works with the state variables instead, and you will see that this system, according to that definition, is stable, but from BIBO stability point of view, it is not stable. So we call this system unstable, but sometimes, just because this system is stable from that point of view, sometimes we call it marginally stable. And this marginal also, it can be interpreted as the fact that if we bring the poles just a little bit to the left, then the system is stable, and if we bring it to the right, the system is unstable. That's for sure. Also, from this definition, if the poles are on the right side, also it is not stable from the Lyapunov point of view. But then if the poles are on the imaginary axis, sometimes we call it marginally stable. But you should remember that from BIBO point of view, it is not stable. So it's not a desirable case that we take into account later. Okay. In the next example, I will consider a second order system. And in this second order system, I consider three different cases when the system has the two poles are in the left side of the j omega axis, or are on the j omega axis, or in the right side. So I'm going actually to investigate the stability of these three different cases. If we apply the step input to a second order system when the poles are in the left side, what you get for the step response, you know that the step response would be an underdamped response. It will converge to the final value, but it will have some overshoot as well. But anyway, from the boundedness point of view, it is bounded because you can find a limit for that. So if you apply a step signal to a system, to a second order system, where the poles are in the left side, so the output is limited. If you apply a step to the second case, when the poles are on the imaginary axis, we saw that before, that it is the output is a pure sine signal. And if you remember, we said that actually the period of the sine wave is 2 pi over omega d, where omega d is the position of the pole on the j omega axis. So this is what you get for the step response. And the interesting thing is that actually the step response of this system is bounded. But I will tell you later why we call this system BIBO unstable, even though the step response is bounded. I will show you why. And if the poles are in the right side, what you get for the step response, actually it is kind of a diverging sine wave which is exploding. So because of that, it is not bounded. So in this case, the step response is not bounded, but in these two cases, the step response is bounded. But if we focus on the second case, in the middle case, I'm going to show you why why we call this system unstable from VIVO point of view. If we apply a sine wave to such a system, so we are talking about this system, a second order system with two poles on the j omega axis, and if we apply a sine wave, and this sine wave actually has the frequency, exactly the same frequency that you had here, so we call this frequency as resonance frequency, which means that if we activate the same resonance, the resonant frequency of the system, we are interested to see what would happen to the output. So input is a sine signal, it is bounded, and if we plot the output, the interesting thing is that actually the output will not remain bounded, it will explode. So we could find an input which is bounded, but the output, that input is not bounded, which means that this system is not stable. So even though it is a very special input, but because we could find it, then the system is not stable. And to be more exact, actually it is the only input that gives you an unbounded output, but still is enough to conclude that system is not stable. Okay, that was for the definition of stability. Also, I showed you some examples whether the system is stable or not, regarding the place of the poles. And also we saw that okay, when we say that the system is stable, it is actually when all poles are in the left half plane, not on the j omega axis, not on the right half plane. They all should be in the left half plane.